this video, we're going to look at what are called measures of variation. So the variance, standard deviation, range, and coefficient of variation. Okay, here they are. What are they useful for? Well, look at these two different data sets. They have the exact same mean. So if we only used a center measure here for these, the mean, let's say, that would not tell us how different these two data sets are. They are very different due to how spread out they are. So this lower one here is very spread out, whereas this upper one here is, or this inside one is very tight or close to the mean. Okay, so two very different data sets with the exact same mean. So yeah, these measures of variation give us an idea of the dispersion of the data values, or the variability of them. Okay, first measure we're going to look at is the range. It's just your largest minus your smallest value. So let's have a look at this data set here. Smallest is 1, largest is 13, so the range is 13 minus 1, which is 12. Okay, and let's just have a look at that in Excel. So here it is, 1 through 13, these guys here. And we just get our max and our min value. So the max, we do an equals max call. The min, we do an equals min call. To get the range, you just take the difference of those two. Beautiful. We're going to talk about the variance and the standard deviation shortly here. Now moving on to the next slide, let's look at these two data sets right here. What do we notice about the range? Well, they have the exact same range. What do you notice about the data though? Are they different? They are different in that these data are much more clustered close to 12, except for that one little outlier there at 7. Well, not an outlier, a lower value, if you will, forgive me. The 120 here is definitely an outlier. The 7 might not be. Now, back to comparing these two. This data set is actually what I'd like to call a uniform distribution. We have the data evenly spread out amongst all of the numbers. So 7, 8, 9, 10, 11, and 12 each have one data point at those values. Range is 5 here, range is 5 here, but they're two very different data sets. So the range really does not account for how the data are distributed. So we can't see that with the range. We also can't see, or it's also, the range is incredibly sensitive to outliers. So these two data sets are the exact same except for the last number. This 120 here is an outlier. Most likely it's probably just an entry error. If you have people input their data, they can often make mistakes. So these two ranges are drastically different, but almost all of the data are the same within the data sets except for that last number. So the range is very affected by outliers. So here are also all the downsides of having the range or using the range to compare variability. Let's look at that in the context as well of those data sets we just looked at. So data sets 2 and 3 here, again, they were quite different data sets, but they had the same range. So again, I just got my max value for each, and I just got lazy and copied this down. You can adjust this range if you want. It doesn't matter if you include blank cells, by the way. And your min, and then you just take the difference between those to get your range. So again, different data sets, exact same range. Now data's 4 and 5, again, same idea. Just get your max value and your min value for each, and then just take the difference between them. So again, very different ranges for these two data sets, even though they're almost exactly the same. Same ranges for these two data sets, even though they're quite different. Okay, so better than that, much better than that, is to look at what's called the variance. So here is the formula for it. If you want, you can practice this by hand. Try this out. So this is the difference between each x value and the mean. Take each of those differences and square them, and then sum up each of those differences, and then divide by how many data there are minus 1. Again, if you want, you can practice that. Now in Excel, that is nice and easy to do. I'm not going to make you practice this formula unless you want to. Later we're going to have to use some formulas like this, but not right now. So let's just use the var.s call. Note there's a var.s and a var.p. P is for population, S is for sample. Assume sample if nothing else is told to you. They kind of almost rhyme, assume sample. So var.s always if you need to get the variance, unless the question specifically, instead of saying sample, unless it specifically says you have a population. Okay, so var.s, back to that here for this data set. okay, is just var.s of those, 14.87. You can just copy that across. Again, I can be lazy and just copy it. I just Control-C, Control-V it if you want, or you can be more precise about it, and actually just go modify your range. Excel ignores blank cells when it's doing these calculations. So note, a blank is not the same as a 0. So if you do mean to have a 0 here instead, enter the 0. If you do not want a data value there, leave it as blank, if that makes any sense. Same idea here and here, var.s for each data set. Okay, var.s for this one, 1.16. And for this one, 559. Okay, so we also see with the variance that it's much, much larger with this one outlier in there. Last thing to look at before we move on to a different data set or different data sets is the standard deviation. And it is just the variance square rooted. So same formula as this guy, but we just put a square root around it. So here it is. Again, you do not need to do this manually. You can just do it in Excel with the following call. Either you can do the following. You can just square root the variance. So square root the variance right there. Or if you want, stdev.s is the Excel call we want to use, and then go highlight your data in question. And again, use .s unless you're specifically told that you have population data. And I just if I have a bunch of data sets in a row here, I just Control-C, Control-V to copy the formula. And it just shifts as I shift over rows here, or sorry, shift over columns. Okay, and then here, I'm going to go modify this one. I believe it goes down to E31. Let's just be sure here. Yes, it does, and I can copy that over. Notice that the standard deviation is getting a little bit better here. They're still drastically different for almost the same data set, but it's not as huge a difference as the range or the variance. These two values are much closer together than 559 and 1, if you will. Okay, now here are the steps for calculating the standard deviation. You don't need to do these unless you would like to do it by hand. It's great to practice these notations. We will be using them later for other formulas, but you don't need to, again, yet. So feel free to follow the steps or feel free to ignore them. Here, looking at this data set, here is the full calculation for these data values. Again, let's just look at that one in Excel here. Here is that same data set. If you would like to get the standard deviation, it's just stdev.s of these data values. So much faster. 4.3095, just like here. Okay, so feel free if you'd like to go get it, but you don't have to get it manually like this if you don't want. Now, let's look at different data sets here. So data A, data B, and data C that have means and standard deviations of the following. Notice they all have the same mean. But what do you notice about the data sets? Are they similar or are they very different? Okay, so data set B is a little bit close to what we call a bell shape or a normal distribution. Data set A is very spread out. Data set C is almost what we call bimodal. It has two different clusters of data here. Very different data sets with the exact same mean, but very different standard deviations. So it's really nice here when we're looking at their standard deviations. It tells us how spread out our data is. So notice that this middle data set has the smallest standard deviation because the data is much more clustered in the middle. These two have roughly the same size standard deviation. They're both almost equally spread out. What the mean and the standard deviation do not tell us is the difference between this type of data set and this one. Okay, so this top one here is fairly evenly distributed, if you will, or more so than this one. This one is clustered around two kind of values, if you will, so it's what we call bimodal. So that we cannot see with the mean or standard deviation. We'll look at other measures later, and we'll also do plots of our data. That's a really good idea, is to graph your data as well to see what's happening with it. Okay, so again, really good to use a standard deviation or a measure of variation to compare your variation in your data. So again, this data set right here has a much smaller standard deviation. This data set right here has a much larger one. And of course, the more spread out the data is, the larger the range, variance, and standard deviation. The more the data is concentrated, the smaller those values. And if the values are all the same, you'd have 0 variation, 0 range, and 0 standard deviation. Note that none of these measures are ever negative. If you get a negative value, you know you've done something wrong. Now, last thing to look at is what's called the coefficient of variation. This is really good to look at when you're measuring different data sets, and it measures the relative variation. Okay, and it's always in a percentage form. Here is the formula. It's very quick to calculate once you've got your mean and standard deviation. So let's look at these two stocks, stock A and stock B. They both have the same standard deviation, but different averages. So if we're talking about the variation in the stock, variations in stocks are very good to look at. That's your fluctuation. That's how much the stock value fluctuates. That's your percent return, essentially. So they have the same percent return, but stock B is worth more money than stock A. So which one is actually more variable? Well, stock A is more variable because it's $5 on 50 instead of $5 on 100. Okay, so the coefficient of variation, very useful to look at when you're comparing different data sets, for example, different stocks that you're thinking about investing in. This one, definitely riskier. You could stand to make more, you could stand to lose more. This one, definitely less risky. Okay, and again, coefficient of variation is the standard deviation divided by the mean times 100. So let's go look at that in the context of these two stocks. Okay, so let's say we have, let's say we have our data A and B, and the coefficient of variation is given by taking the standard deviation and dividing by the mean. So we just do that for both of them. And then in Excel, it's nice to change them to the percentage form. There we go. So 10% and 5%. Okay. And let's look at one last example for this video. Let's also look at a stock C. Note that it has a very different mean price than stock A. And so its standard deviation is smaller for stock C, but so is its mean. So which one is more variable? Well, stock C is actually still much more variable. It has a $2 standard deviation, but compared to the $8 value of the stock, that puts us at 25% variation for stock C. So again, it's so good to look at this coefficient of variation if you're comparing the variation in data sets. Go get this percentage variation, if you will, by getting this coefficient of variation. That concludes our section on variation. Thanks for watching.